Let's peel back the cover on the tools and tech that shape our world. Ready for a deep dive? This channel is your backstage pass into the fascinating universe of big machines, smart products, and next-level tools. We break down the mechanics behind everything from industrial robots and circuit boards to power tools and DIY repairs. Curious about how things work, how they're made, or even how to fix them. Right. Ever wonder what your graphics card is actually doing while you're gaming, editing, or training AI? Let's break it down, one clean layer at a time. A graphics card, GPU, is a specialist, not built to do everything, built to do one thing insanely fast. Crunch thousands of similar math problems at the same time. Think massive teamwork. Inside the GPU are thousands of tiny cores. CUDA cores on NVIDIA, stream processors on AMD. Each one is simple, but there are a lot of them. They run in parallel. Same instructions, different data. That's called SIMT, single instruction, multiple threads. It's like a stadium crowd doing the same dance, each person in their own seat. So how does that draw a picture? Start with a 3D scene. Models made of triangles, lights, textures, and a camera. Your engine or app sends commands through an API, DirectX, Vulkan, or OpenGL. The GPU takes the job and runs it through a pipeline. Stage 1, vertex shading. Vertices, the corners of triangles, get transformed from model space to screen space. Math happens. Matrices, rotations, perspective. Optional steps like tessellation subdivide big triangles into smaller ones for smooth curves, and geometry shaders can add or tweak shapes. Next, rasterization. This is where 3D triangles become 2D pixels, and the GPU figures out which pixels each triangle covers. Then fragment, or pixel, shaders run per pixel. They decide color, read textures, compute lighting, shadows, reflections, and fog. Texture units, TMUs, grab and filter texels from VRAM and feed the shader. Render outputs, ROPs, blend, depth test, and write the final color to the frame buffer. Do that for millions of pixels, 60 times a second or more, and boom, a smooth image. VRAM matters a lot. It's the GPU's local memory. Big textures, geometry, shadow maps, and frame buffers live there. More VRAM gives more room. More bandwidth feeds cores faster. Think Buffett line. If it's slow, the cores wait hungry. Higher clock speed equals more operations per second, more throughput. But heat is the enemy. Fans, heat pipes, and vapor chambers keep it cool so it can boost. Power limits and cooling decide how long that boost holds. Modern GPUs add specialty hardware. Ray tracing cores accelerate realistic lighting, rays bouncing shadows and reflections. It's heavy, so AI upscalers help. Tensor cores run neural nets like DLSS to upscale lower-res frames to look like higher resolution, saving performance. AMD and Intel have their versions too. Drivers are the translators. They take API calls, schedule work efficiently, manage memory, and optimize shaders. Updates can unlock performance or fix bugs because the pipeline is software plus hardware working together. GPUs aren't just for games. The same parallelism chews through video encodes, simulations, and machine learning. Compute shaders skip the raster pipeline and just run math on big data grids. If a job can be split into many small, similar tasks, the GPU loves it. What bottlenecks you? Sometimes it's the CPU feeding draw calls. Tons of tiny objects can choke the command stream. Sometimes it's VRAM. Oversized textures trigger stutter. Sometimes it's bandwidth, high resolutions, and ray tracing slam memory. Tune the right limit. Drop resolution or ray tracing for shader load, reduce texture size for VRAM, and simplify shadows for ROP pressure. One line, the GPU is a parallel math beast that takes 3D scenes, runs a shader pipeline, and blasts frames to your screen. Fast. Shopping? Look at core count and clock, VRAM size and memory bandwidth, ray tracing and AI upscaling support, plus power and cooling. Check driver reputation and the games or apps you use. Why one card wins, not just cores, architecture efficiency, memory, drivers, and how your workload maps to the pipeline.